our problem 4 on rotational motion. And this one is a little bit different. I have a small satellite, mass ms. And this satellite travels in a circle of radius r1. So I will place it here. This is my satellite. Okay? It is traveling about the Earth right at the center. And Earth is assumed to be fixed. The force exerted by the Earth on the satellite is the usual gravitational force, which is attractive. The force is attractive force. And this force has magnitude of gravitational constant product of masses divided by distance r between the Earth and the satellite, distance squared. Now, what do they ask us to find? First of all, they ask us to find the potential energy function for this gravitational force, first. And second, how much work would this force do if this satellite were somehow moved from point r1, radius r1, theta 0, to another point with another orbit, and to the point with r2 and pi over 2. All right, so what do we do? Step by step. Let's start with the potential energy function for the force F. What is the potential energy function? Which formula to use? We already covered the potential energy function. Now we work with polar coordinates. That's the difference. So let's introduce our coordinate system. What is it? Remember, we have always IR out of the circle. This is IR. Then I theta will be tangential. And instead of doing tangential, I did something very strange. So I erased this. And I will draw tangential. So this is my IR. And I theta is perpendicular to IR. Both of them are supposed to have the same length, I theta. IR, I theta, perpendicular to IR. And if I have my coordinate system, I can immediately write this force in terms of components. What are the components of this force in my coordinate system? I have non-zero F sub r, which is minus. Force is attractive force towards the center, and my r is out of the center. So it is minus. Projection is negative. G, M, E, M, S over distance between them squared. What is F theta? F theta is 0. There is no theta component. This force is in radial direction. So it looks like we work just with one dimension. Remember the formulas. If we work just with one dimension, we can use a simple formula to find the potential energy function. Why? Because F sub r is equal to minus du, the potential energy function, dr. And if we take the indefinite integral of both sides of this equation, as we did in the module on the potential energy function, what we will have? We will have the potential energy function u. And I bring this minus to another side of this equation, integral f r dr. Step by step, I keep this minus, and then it is integral. And what is f sub r? F sub r is also negative, so he is minus g, and then me, ms, divided by distance between them squared, dr. I will put the line here, and let's take this integral. Minus minus plus. I take all constants out of this integral, g, me, ms are all constants, and dr over r squared gives me minus 1 over r. Minus 1 over r. And I'm using indefinite integral plus constant, and this is my potential energy function. Potential energy function for the gravitational force is minus G MEMS over R. We solved half of the problem. Find the potential energy function for F. Can you do it using the definite integral? Absolutely, you can do it. I just decided to go this short way to do that, since we have just one component of force, radial component. Part B, find the work done by this force if this satellite is moved from this point to another point. So, do we see an angle here? No, nothing depends on angle in our formula. But what about work? Remember, what is work? Work done by conservative force, and this is a conservative force with this potential energy. Work done by conservative force is minus change in potential energy function. U at the final point, U at our point R2, and there is no any dependence on angle, so I will skip it, this angle. It's irrelevant. U at R2 minus U at R1. Okay, I already know my potential energy function. I already calculated it. All I need to do, just find it at R2 and at R1. If I write it here, can you see it? I think yes. So minus, I open the brackets. This minus comes from the definition of the potential energy function. Now it is minus, and then I have minus G ME MS divided by R2. I plug in R2 minus this minus and minus give me plus G ME MS divided by R1. Okay, and the final line, I will redistribute this minus. So minus minus plus, and then this will be minus. So what do we have? We have G with plus. Can I just factor out G ME MS? I'm running out of space. So I factor out G ME MS. And then what do we have in our brackets? It will be minus minus plus 1 over R2. And then it will be minus 1 over R1. Does it make sense to us? Is it positive or negative? R2 is greater than R1, so this is negative. Work is negative. Does it make sense? Yes, because this force is towards the center, and we are moving this satellite to this larger R2. So the force and the displacement are in opposite direction. Work done by this force with this displacement has to be negative. And it is. We solved the problem. Now imagine that you want to find this work when done by this force when you move this satellite from this point to this point without using the potential energy function. Can you just calculate work using our formula? Work is definite integral. We are moving from point R1, 0 to point R2, pi over 2. And I have to write here F dot dr. This is my definition. Work done by force F. So what is this dot product? F dot dr in polar coordinates. I can write force as FRIR, force as FRIR plus F theta I theta. I can write dr, and you probably remember this from your calculus class. Vector dr is dr IR plus r d theta I theta. And if you forgot it, it should make perfect sense to you. Just think about it. Divide each of these guys by dt. So then dr dt, dr dt, this is our VR, radial component of velocity. What is here? R I divide by dt, r d theta dt. This is r omega, our tangential component of velocity. So hopefully it all comes together. You remember this. And then if I take this dot product, then I will have integral IR dot IR will give me non-zero dot product FR dr. And I will be moving from point R1, 0, to R2. And of course you can do it for any point. R2, pi over 2. And then plus IR dot I theta, 0. I theta dot IR, 0. And another non-zero will be integral F theta, R d theta, R d theta. So for this problem, again, I'm moving in from R1, 0 to R2, pi over 2. The limits for different problems will be different, obviously. So what is our F theta? Our F theta in this problem is 0. There is no theta component of gravitational force, so we can ignore this part of the integral. We just take F sub r dr. Let's do it and figure out if we get the same answer. So work is equal to integral. Nothing depends on angle. There is no angle in this formula, so I ignore angle. I just put this integral from R1 to R2. F r dr. What is my F sub r? The projection of FR is negative with my choice of IR. So it is minus G, constant. MEMS, constants, over R squared, variable. dr, I integrate with respect to r. Let's take this integral. dr over r squared will give me minus 1 over r. Minus minus plus, so I have G. And then MEMS over r. And the limits are from R1 to R2. And the last step, we need to plug in our limits. Ready? Let me factor out this guy, G, M, E, M, S. And then what do I have in parentheses? Upper limit, 1 over R2, minus low limit, 1 over R1. Do you see what's going on? I put this parenthesis instead of brackets, but the rest is the same. So this way or that way, we calculated work done by this gravitational force when we moved our satellite from orbit R1 to orbit R2, and angle was irrelevant. And of course it is negative, and we understand why. Force is towards the center, displacement is out, further away from the center. I think we solved it.